It's a really great pleasure to have Danilo Marchesini here. He got his PhD in JS in Italy, and then he went on to become a postdoc at Yale, which is where I met him. I'm not even going to say how many years ago. Then he moved on to Tufts, where he is now an associate professor in the department, and today he's going to tell us about massive galaxies.
Thank you all for having me here. So today I would like to share with you results that my collaborators and I have published in the last 2 or 3 years on the assembly of today's most massive galaxies over the past 12.8 billion years of cosmic history, basically, from redshift of 7, roughly speaking. And I should warn you, some of these results are still very controversial, so you're free to reject them or criticize them as much as you would like. I would like to first off thank all my closest collaborators listed here. In particular, I would like to highlight the contribution from the Tufts research group. In particular, to graduate students Jamila Marsan and Nick Martis, and Jamila is actually finishing up in July and moving on with a postdoc in Canada. Also, two extremely capable undergraduate students, Erin Kadofong and Daniel Lengebegel, both of them will start grad school in September. And then the two postdocs, Ryan Cybulski, who's been mostly working on the NMBS-2, which I'll talk about later, and Heath Shipley, whom you know quite well, I believe. I would like to keep this talk very informal, so please feel free to interrupt me anytime to ask for questions, especially the students that are in the audience. I will not bite, I promise. All right, so for those of you who do not know where Tufts University is, I honestly didn't know before moving there myself, so I don't blame you. So it's in Massachusetts, right here in Boston. It's actually within the greater Boston. Here is it's Boston downtown with the historical landmarks. Down here, there's Harvard, CFA, who you might be more familiar with. And Tufts University is just a couple of stops on the red line going north-west. And yeah, we're pretty close to them. We have a very small, especially compared to the size of Texas A&M. We're a small campus, but it's quite pretty. It's right on the tallest hill in the vicinity of Boston. So we have a beautiful view of the Boston skyline. And we're really the only university in the Boston area who can look down on Harvard. Just physically, but I strongly encourage you to come and share, experiment that feeling of being able to do that from the top of our hill. Anyway, we are a very young astronomy program. It's only 7.5 years old, basically when I first arrived there. But it's actually quite active and growing. And we now have 3 postdocs, 3 faculty, 6 grad students, and several undergraduate students who are very active in reading our research programs. And it's still not official, but Tufts has decided to join the Prime Focus Spectrograph at Subaru, so that's pretty much the only investment in the history of the university in astronomy, so we're all very, very excited. All right, let's move on to the talk. So in the local universe, 13.8 billion years after the Big Bang, we see that galaxies do not look all the same. They show very distinct morphological features. They're well represented by the Hubble's tuning fork, with ellipticals at one end and spiral galaxies at the other end. And sort of understanding how these different type of galaxies formed, or in other ways, understanding the physical processes that are responsible for shaping galaxies into their present form, is really one of the major unsolved problems in astrophysics, and one of the I would say one of the most controversial questions in galaxy formation and evolution is how and when today's most massive galaxies form. And they're shown here with this very massive elliptical galaxies, and I'll talk more about them in a couple of minutes. And so I guess the working hypothesis for galaxy formation and evolution is that galaxies form under the influence of gravity, and galaxy formation can be seen sort of as a two-step process. First, you have the dark matter, which is shown here as sort of blue in this simulation from the illustrious model. And so the gravitational pull of the dark matter is responsible for growing the tiny seeds in the matter density distribution that we infer from the cosmic microwave background radiation when the universe was only about 400,000 years old. And then with time, these seeds grow bigger and bigger, and as they grow bigger, gravity is able to attract additional matter easier onto it. And with the growth of these dark matter structures, also gas is being pulled together, and now the color represents the gas temperature, and sort of white, red is very hot, and blue and green is cold. And gas, which is made of hydrogen and helium, is the primary ingredient for the formation of stars, and so it's the primary ingredient for the formation of the stellar content of galaxies. And so these simulations, which now have reached a very high level of sophistication, have in a way shown us that galaxy formation and evolution is a very complicated process which involves many physical processes that unfortunately are still quite poorly understood from a theoretical perspective. So ultimately, we would like to know in great detail the recipe of how galaxies form and evolve. And in particular, this talk will be focused on the most massive galaxies that we see in the local universe. And I think it's fair to say that today we sort of have a pretty good picture of what all of the ingredients that go into that big pot to make to cook the galaxies. Some of them I already mentioned, and there's dark matter, there's gas, and one ingredient is how gas cools, and the star formation process itself. We have merging of galaxies. We have to add different feedback mechanisms. One is stellar feedback, so supernova explosion, stellar wind, but also heating from stellar remnants. We have AGN feedback, another ingredient, still not very well understood, but it comes in different modes, at least two, quasars and radio mode. And then we can add all sorts of environmental effects to the pot, and there are all others that are more or less understood. And again, the idea here is that we would like to ultimately find the exact way of mixing and introducing all of these ingredients at the right time in the right amounts, and so on. And so the ultimate test to assess whether or not we've been able to put together a recipe for the formation and evolution of galaxies to compare what the simulation predicts to what the real universe tells, the observations of the real universe. And so if we look at the local universe, if we look at the properties of the most massive galaxies around us, we see that they constitute a pretty homogeneous population. This is a pretty crowded slide that I will walk you through slowly, I suppose. So the first thing that we see here, this is the rest frame color versus stellar mass. It's the color stellar mass diagram. And these greenish bands sort of represent the range in stellar mass of what I call today's most massive galaxies. Around 11.8 of 6 times 10 to the 11 solar masses. But you see that these very massive galaxies tend to have very red and similar colors, rest frame optical colors, and they populate the extreme massive end of the red sequence of quiescent galaxies, which is very clearly shown here with the blue cloud of star-forming galaxy over here. If you look at the age of their stellar population, you see that they're typically characterized by all stellar population with a pretty small dispersion of about 20%, so plus or minus 2 billion years of age. So this is important because that means that most of the bulk of their stars formed in the redshift range between 1 and 4. They are characterized by early type morphology. This is the stellar mass function. This is stellar mass, and here is a stellar mass function split into 3 different morphological types. And so early type are sort of disky, early type spheroidal, so ellipticals and zeros, and then spiral galaxies. And you can see that the most massive galaxies are dominated by the early type spheroidal galaxies. They are characterized by quiescent stellar populations, given their D4000 and H delta measurements, and they tend to live in over dense environments, as shown again by the stellar mass function split into different environments. And so they tend to populate environments of clusters and rich groups. However, there is this survey, recent massive survey that looked at a complete sample of very massive galaxies within about 110 megaparsec, and they actually do show that about 20% of the most massive galaxies are groupless. Okay? So it's not that all of them live in rich environment. Archaeological studies of galaxies in the local universe have shown what we now refer to as downsizing. Basically, more massive galaxies today massive form most of their stars at earlier times, and also the duration of the star formation period must have lasted for a shorter amount of time for the more massive galaxies. So if we look at the most massive galaxies today, they must have formed most of their stars in the first sort of 3 billion years of cosmic history, so redshift above 2, and the duration of that activity should have lasted for less than 1 billion years and as low as maybe a couple of hundred million years. And so if we put in sort of all of this information together, now a decade ago, there was all of this provides sort of evidence for an evolutionary scenario for the formation of massive spheroidal galaxies by redshift of 0, which is sort of depicted by this sketch in the rest frame UV stellar mass diagram, where you have early star formation and mass assembly, and during this phase, arguably the progenitors of today's most massive galaxy would look like probably in the blue cloud of star-forming galaxies, and then quenching happens, they migrate onto the red sequence, and they age, but also they continue to grow, perhaps due to dry merging within the red sequence itself. And so one way to test this scenario is actually to go back in time and look at the progenitors of today's most massive galaxies and see what they actually look like. And so this is a work now, I guess, 3 years old of mine, in which the main goal was to look at the evolution of the properties of the progenitors of today's most massive galaxies over the last 11.4 billion years since redshift of 3. And so the first thing you want to do is to find, select the progenitors. And here I'm showing, oops, excuse me. And here I'm showing the cumulative number density as a function of stellar mass. The cumulative number density are derived by integrating the stellar mass function of galaxies. In this specific case is from the mass function of derived with the ultravista DR1. And this cumulative number density, the different colors show different redshifts. So the lowest is 0.2 to 0.5, and all the way to 2.5 to 3 in red. So if we assume that galaxies conserve their rank order in mass through cosmic time, we could select progenitors of a certain population that a redshift, let's say 0, has a certain fixed cumulative number density. And again, if the rank order is conserved, then that fixed cumulative number density should be the same at earlier times for the progenitors population, and so we can select progenitors around the stellar mass that were in which this sort of dashed line intersect these curves. Now the problem here is that galaxies merge, and because of galaxy-galaxy merging, we have that the mean cumulative number density of a certain galaxy population changes with time. And so basically one way to account for this is using this sort of semi-empirical approach using abundance matching. And so effectively what you want to do instead of using a fixed cumulative number density is use a cumulative number density that increases as you go back in time to account for galaxy-galaxy mergers, because back in time there were more galaxies were more numerous than today. And so by doing this, we can select progenitors of today's most massive galaxies. And here I show the average, the evolution of the typical stellar mass of the progenitors of today's most massive galaxies since redshift of 3. And from now on, my working definition of ultramassive galaxy of redshift 0 is a galaxy that has a stellar mass today of about 6 times 10 to the 11 solar masses, or 11.8 in log scale. And so you can see that over the 11.4 billion years since redshift of 3, the progenitors have grown by a factor of about 3.5 in stellar mass.
It's really only about 10 times more massive than the Milky Way.
You mean at this time? Oh, this one?
Yeah.
Yeah. Or a little more, depending on which specific
It's
estimate
on
is.
100. So you're talking about, we just for context, an ultramassive is still nominally within a factor of 10 of the Milky Way.
Yeah. If you go back to the mass function that I showed before, here, for example, this sort of dashed green area is what we call ultramassive today, but the Milky Way, it's somewhere here, around the knee of the stellar mass function. Again, it depends a little bit on the exact definition. And, a small change in mass here, it's a huge change in density. It's a good point.
So you said that some of the most massive galaxies in the local universe are groupless, but not really at these masses, right? I mean, these things pretty much only exist.
Well, actually, the survey selected all galaxies within 110 megaparsec above 11.5 in log scale.
Okay.
So I don't know exactly if those 20% might be at the lower end of that range, but they're really massive anyway. So, and it's something that you go to conferences and you always hear, most massive galaxies are in cluster or rich groups, but strictly speaking, not all of them are, majority.
So even at redshift almost 3, 11.2 is still would be a red galaxy today, isn't it? So are these mostly dry mergers, probably?
I'll get back to that point, yeah. But it's a good point, and also, even at redshift 3, they're already quite massive.
Yeah.
Casey, did you have a question?
Right, John, you took off. No, I was going to agree with you. These things still getting massive. We're talking about things at the center of Coma or Virgo today. I mean, those galaxies at the center of, N87 will be in this mass range today.
Yeah, I think strictly speaking, sort of the very, very, very most massive VCGs, I think, are in the upper, like 10, they get to 10 to the 12.
Yes.
Yes, right.
But that's about it, yeah.
Yeah, these are these weird, supermassive monsters, for example.
Yeah. Yeah, so again, already at redshift 3, they're pretty massive, at about 11.2. And I'll come back to this point later, especially on how they grow in stellar mass within this time frame. All right, the one thing I want to focus now is on the study of their stellar population properties. And here I'm showing the rest frame UMAN-SV versus rest frame UMAN-SJ color diagram. I'll keep referring to this as the UVJ diagram. And it's become a very powerful tool in the last few years to separate quiescent galaxy in this box here, and you can see them there, and star-forming galaxy down here. And this is because by using these two colors, you can separate the galaxies that are red because they're quiescent from the galaxies that are red in the red stream UV because they are dusty but star-forming. And here is the UVJ diagram in the different redshift beams that I showed before. The lowest one, 2.2 to 0.5, all the way to 2.5 to 3. Here, the grayscale representation shows the overall galaxy population at those redshift in a stellar mass complete sample. And the red and the blue points represent the quiescent and star-forming progenitors, respectively, of today's ultramassive galaxies. And so the first results that you can see here is that a redshift below 1, all the progenitors are quiescent. So that means that they have quenched by a redshift of 1. And the other thing that you can see is that as you go to higher redshift, the contribution from star-forming galaxies to the progenitors population increases with redshift, and a redshift between 2 and 3, the majority of the progenitors are dusty star-forming galaxies. They're dusty because they are in this sort of upper right part of the star-forming box. And I'll come back to this in a second. The other thing that is very interesting to see is a clear aging of the stellar population of the quiescent galaxy. You can see this in two ways. First one, if you look at the red point, again, the quiescent progenitors, you see that a redshift 2.5 to 3, they sort of live in this sort of left bottom corner of the UVJ wedge. And with increasing cosmic time, they migrate to the upper right part of that box. And that's very much because of aging. The other way to see that is if you look at the average spectral energy distribution of the quiescent progenitors, you see that a redshift 2.75, the average SED of those quiescent galaxies is this red curve, which is typical of a young post-starburst galaxy with a little bit of dust, but very strong Balmer break. And with cosmic time, that evolves into a spectral energy distribution that is typical of a quiescent maximally old galaxy without any dust. Another thing is, as I mentioned before, is that the star-forming progenitors are actually quite dusty. From the position of these progenitors in the UVJ diagram, there's typically 1/3 magnitude of extinction in the visual band. But also their dusty nature is confirmed by the almost ubiquitous detection of these galaxies in the 24 micron data, which are represented by this green dots. So the first takeaway point, the point that I would like you to take away is that when we look at the progenitors of today's ultramassive galaxies at redshift 2.5 to 3, the majority, 85% or so, are red, heavily dust-obscured, highly star-forming galaxies. And so they're characterized by typically 1/3 magnitude of extinction in the visual band, star formation rates of a few hundred solar masses per year, and they're really quite massive, 2 × 10 to the 11 solar masses. Now, the increasing role of dusty galaxies in the population of massive galaxies as you go to earlier time was very nicely shown recently by a letter published by a PhD student, Nick Martis. He used the combination of 3D HST catalogs and UltraVista DR1 to look at the evolution of the fraction of quiescent galaxy, relatively unobscured star-forming galaxy, and dusty star-forming galaxy as a function of stellar mass. And here is basically how he selects the 3 populations. So now the color coding in this UVJ diagram is as a function of extinction in the visual band. And so again, you have the quiescent definition here, but then he split the star-forming population in relatively unobscured and obscured, star-forming galaxies. And basically, the idea here was to separate using an AV of 1-ish And you can see from these plots that the ridge of AB1 sort of follows this dashed curve line. So that was the working definition here between unobscure and dusty star forming. Here I show the fraction as a function of stellar mass of the quiescent galaxy, the unobscure star-forming galaxy, and the dusty star-forming galaxies. Again, the colors represent the different redshift from the lowest redshift, 0.2 to 0.5 in blue, all the way to 2.5 to 3 in maroon. And so if you look at the first panel, well, you see what we already knew in a way. You see the buildup of the quiescent population with increasing cosmic time. This buildup is fastest at the highest, at the largest stellar masses, and sort of the slowest around 10.3 in 2 times 10 to the 10 solar masses. What's a little bit more new is that if we look at even lower stellar masses, we see that the buildup is actually quite fast as well. And perhaps this is a consequence of potentially environmental effects kicking in that are affecting more the low mass galaxies. And as we look at the lowest redshift beams, we see that the lowest stellar masses below 3 times 10 to the 9, we see sort of the quiescent fraction to plateau, and perhaps again this is evidence for over quenching environmental quenching. If you look now at the star-forming population, you see the opposite. You see the unobscure star-forming galaxy to decrease in relative importance within the galaxy population as you go to lower redshifts, so increasing cosmic time. The unobscure star-forming galaxy completely dominate the galaxy population at the low mass end, but then with increasing stellar masses, their relative importance drops very rapidly. And it's kind of interesting to see that the stellar mass that corresponds to the transition, above, below which the unobscure star-forming galaxy dominate, the number counts sort of decreases with increasing cosmic time from 2 times 10 to the 10 solar masses, a redshift 2.75 to about 5 times 10 to the 9 at the lowest redshift. Now, if you focus now on the third panel, the dusty star-forming galaxies, you see that a low redshift, sort of below redshift 1.25, which are these bluish curves, you see that the dusty star-forming population is relatively important only at intermediate star masses, between 10 and 10.5 in log scale. But at those low redshift, their importance really drops pretty dramatically at both high and low masses. But then with increasing redshift, a redshift above 1.25, you see how the importance of dusty star-forming galaxy really grows very rapidly as a function of redshift at the high mass end. And at the highest mass range that we were able to probe around 11.5, it's about 60% contribution from dusty star-forming galaxies, and their fraction basically dropped by a factor of more than 30 from that highest redshift all the way down to sort of the local universe.
So, I'm sorry, maybe you said, is it based on the horizontal dotted line? Is there?
Oh, it's just the 50% line,
Okay.
sorry. Yeah, so above you have the dominant role of that galaxy population. I need to tell my students to make the labels a lot bigger in their papers. Rule number 1 for faculty, I guess. So again, at the high mass end, the massive star-forming galaxies are predominantly dust obscured in the early universe, which is sort of the first takeaway point here. In a similar way, you can see this here, where now within each redshift beam, I'm comparing the fraction as a function of stellar mass of the unobscure, the dusty star-forming galaxy, and the quiescent galaxies. And so again, a redshift a low redshift, you see that the dusty star-forming galaxies are relatively important only at intermediate stellar masses, but then their role rapidly increases as you go to higher redshift, and a redshift above 2, that really represents sort of the 50–60% of the massive galaxy populations above 3 times 10 to the 10 solar masses. The other thing that I would like you to take away from here is that when you look at the massive end, above 10 to the 5, again, 3 times 10 to the 10 solar masses, the high mass end is always dominated by red galaxies. They're red either because they're quiescent, as is the case in the low universe, the low redshift universe, or they're dusty star forming, as it's the case in the high redshift universe. Another question that you might ask is, what is the relative contribution of the dusty star forming galaxy within the overall star forming population? And this is shown here as a function of stellar mass, is the ratio between the number of dusty star forming galaxies over the number of non-dusty star forming galaxies. And you see that above, again, 3 times 10 to the 11 solar masses, the non-dusty star-forming galaxies are a factor of 3, 5 more numerous than the unobscured star-forming galaxies. And what was really surprising is that there's only a mild dependency on redshift on this. There's a little more in this paper, but I will not bore you to death. I found it very, very interesting. Let me move on to the environment of these progenitors. And this is a work that Benedetto Vulcani and I have done, published last year. So this is the results, sort of the main results on the environment. The other main result is how these progenitors have grown their stellar mass. Unfortunately, we were able to do these, both of these investigations only out to redshift of 2 because of the depth of the DR1, the Ultra Vista DR1. But we're now extending that to higher redshift using the much deeper DR3. Here, basically, what you see are stamps centered around the progenitors of today's ultramassive galaxies, and the size is basically 500 kiloparsec. And the different rows represent different redshift, from the lowest one, 0.3, 0.4, 0.7, 1.3, and 1.7, 1.8. And so what you can see here is that the progenitors of today's ultramassive galaxies reside in a pretty large variety of environments. And so, for example, in the first column, you see that the progenitor is really isolated. There's not much companions around it at all. And then in the last column, you see an example where the progenitor is surrounded by 10 of companions. So that's something that is pretty cool. There's more on the environment, but again, there's a lot of these results that I'd like to share with you. So, the other thing is, here you can see the cumulative mass fraction as a function of redshift. Basically, it's the relative contribution of star formation in green and merging in red to the growth of these progenitors since redshift of 2. Now, the contribution from star formation and merging were estimated, derived independently, but it's nice to see that when the star formation is derived from the combination of the UV and the infrared, which arguably accounts for dust obscure star formation, we see that the combination of star formation and merging is able to account for most of the growth in the stellar mass that we infer from the abundance matching approach that I showed at the very beginning. And so the other sort of takeaway point here is that the contribution from merging to the growth of the stellar mass of these progenitors, at least since redshift of 2, is really dominant at redshift below 1. This is in a way not that surprising, given that I showed you before at the beginning that all of the progenitors were quenched by redshift of 1. And the growth from star formation is really dominant at redshift above 1.5. And so putting it all together, I guess all of these results suggest sort of a refined evolutionary path for the evolution of today's ultramassive galaxies since redshift of 3. And this evolutionary track is shown by this green line, and it involves rapid growth of the stellar content of this galaxy through a short and very intense dusty burst of star formation. And during this phase, the progenitor would look like red, heavily dust-obscured, star-forming massive galaxies. And after the quenching, their stellar population ages, and they migrate slowly onto the red sequence, or the red sequence of those redshifts. And by redshift of 1, all of the sort of growth due to star formation has been terminated, and from redshift 1 on, the dominant mode of growth is because of merging, and ultimately they reach their position at the extreme massive end of the red sequence. Now, I guess the next question is, what happens at redshift above 3? What are the progenitors of these galaxies at even earlier times? And I guess the answer for this question has its roots in this now pretty dated paper of mine. It goes back to 2010. Here I used the Newform Medium Band survey to look for massive galaxies in the redshift range 3 to 4. You must be very familiar with the Z-Forge survey, I hope. Basically the NMBS was a precursor of the Z-Forge over a wider area, but not as deep as the Z-Forge, but it used these medium band filters in the J and H and near infrared bands. And so back then I was able to find a little bit more than a dozen of galaxies at redshift 3 to 4 with stellar masses above about 2 times 10 to the 11 solar masses, which is the completeness in stellar mass from the NMBS. And this was, this basically provided one of the first robust evidence for the existence of very massive galaxies when the universe was only 2.5, 3 billion years old. But also it provided evidence for a large diversity in properties for these galaxy population. In fact, some of these galaxies were consistent with being already quiescent, and others were very highly star-forming with several hundred solar masses per year. Oops, sorry about that. And Z-Forge was able to really extend this to even lower stellar masses and found very, very similar results. What was surprising back then, at least to me, was that the majority of these very massive galaxies at redshift 3 to 4 were detected with high confidence in the RIMS 24 micron data. In fact, their sort of guesstimated total infrared luminosity was way into the hyperluminous infrared galaxy regime. And so it's either these galaxies were still very actively star-forming galaxies, but also very obscured, and they were harboring dusty, obscured AGN. And I'll come back to this in a second. What was nice, because this sample was a stellar mass selected sample, you can actually, one galaxy would turn out in the cosmos to be a 7-millimeter galaxy. And so you can easily and very directly estimate sort of the duration of an intense dusty starbursting phase if you assume that all of these galaxies have to have gone through that phase. And it came out to be about 60 million years, plus or minus, well, plus 150. But this is in very good agreement with independent estimate of the duty cycle of the 7-millimeter phase from other estimates that make a lot more assumptions. Now, despite the well-sampled SEDs of the NMBS, there was still quite a bit of ambiguity in the photometric redshift solution for at least half of the sample. Those galaxies could have been a lower redshift, between 2 to 3. And so Jamie and Marsan, PhD student at Tufts, has led a spectroscopic follow-up program on these very massive galaxies at redshift 3 to 4, and this is the very first confirmation of a very massive galaxy at redshift 3.35. This is now a year and a half, 2 years old. Here you see the beautiful spectral energy distribution of this galaxy. We dubbed it the Vega galaxy because its spectral energy distribution is very reminiscent of the spectral energy distribution of the star Vega. But after you correct for emission line contamination and potential AGN contamination, this has a stellar mass of 3 times 10 to the 11 solar masses. It's not quiescent yet. It has a few solar masses per year of star formation, which account for this UV emission. But if you look at the specific star formation rate in log, is about -11. So really transitioning from star forming to quiescence. It has no dust, and it has a stellar age of about 400 million years with a very short duration for that star formation. If you look at its position in the UVJ diagram, it's here in green, and it's very consistent to evolve from redshift 3.35 by the time it goes to 2.5 to 3 into these red points, which are the quiescent progenitors of redshift 2.5 to 3 of today's ultramassive galaxies. And this is quite interesting because before I showed you that most of the progenitors of today's ultramassive galaxies are actually in this area of the UVJ diagram. They're dusty star-forming galaxies. So perhaps there's two ways of getting into here. This galaxy was observed with HST in the ACS and the WIPC3, and it's very small, 1 kiloparsec effective radius, already sort of a elliptical morphology, and this really makes this galaxy one of the densest in the early universe. This is the Vega galaxy down here with 11.5 and 1 kiloparsec. And it's it's not as small, but density-wise, it's comparable to this very recent confirmation of, I suppose, the first quiescent massive galaxies of redshift 3.7 selected from Z-Forge. This is a factor of 2 less massive, but also really tiny, just half a kiloparsec effective radius. What was also quite nice is that this galaxy, despite no indication of a lot of star formation in the rest frame UV to near infrared, it was very bright in the MIPS 24 micron, as I mentioned before. But then you look at the Herschel data, and you only find upper limits at best, a couple of sigma detection in the Spire data, and so you can rule out that the MIPS flux, the MIPS light, is dominated by obscure star formation. In fact, we can put some lower limits from an obscure AGN of 60% and above. And so this galaxy is really sort of a prototype object of a very massive galaxy, very dense, very compact, almost post-starburst galaxy that form most of these stars in a short and intense burst of star formation at a formation redshift of about 4.1, and now hosting a very powerful AGN, luminosity of about 2 times 10 to the 46 ergs per second, and AGN that perhaps is responsible for the quenching, though it's hard to say that. Just a couple of weeks ago, Jen resubmitted the paper presenting the other galaxies of the follow-up program in a staggering number of 5. Still low statistics, but nonetheless, she was able to confirm the existence of numerous massive galaxies redshift above 3, with stellar masses in the range between 2 and 4 times 10 to the 11 solar masses per year. And also, if you look at them in the UVJ diagram, it's the colored points, you see again a large variety, a diverse range of stellar ages, star formation rates, and extinction. And applying the same analysis as shown before to the infrared, again, all of these are very bright in the MIPS 24 micron, yet they're not. Most of them are not detected in the Herschel data, except maybe this one in the sort of the Lewis Spire bands, and this is the sun-millimeter galaxy, so they better be detected in the infrared. But the bottom line is that using the same line of argument that I said before, about 80% or above of these galaxies are hosting unobscured AGN. And in fact, you have to be very careful to use the MIPS fluxes to estimate star formation rate, because they're going to be contaminated heavily by the AGN. So you have to correct for that. Also, 3 of these galaxies are X-ray sources, so X-ray AGN, and one, the submillimeter, is also a radio-loud AGN. So we're taking this a step farther, or at least generally did, and trying to properly model the spectral energy distribution, including also the AGN component, both in the infrared and in the rest frame 0.1 to 1 micron. And again, it turns out that at rest frame wavelength between 1 and 30 micron, the AGN contribution is very large, from a minimum of 40% to, in some of these cases, like these 2 and these 3, it's as high as 100%. Whereas the contribution in the rest frame 0.1 to 1 micron is pretty minimal. And so because of that, the AGN light does not bias significantly the stellar masses estimated in these objects, except for this galaxy, the submillimeter galaxy. You have to do this properly, otherwise you would estimate the stellar masses quite a lot. All right, here I guess I'm putting it all together for this work, where I show the evolution of the fraction of the AGN as a function of redshift in galaxies more massive than 10 times 10 to the 11 solar masses. And you can see how the AGN fraction is sort of constant at about 30% all the way out to redshift 2-ish. But then a high redshift, it really skyrockets to 80% or above. And it's interesting that this transition seems very rapid between redshift 2 and 3. Actually, the gray points here are from the Z-Forge. Might be familiar with this very nice piece of work. And so the point here is that, again, perhaps a redshift above 2.5 or so in this massive system is really when the supermassive black hole at the center of this monster galaxy are pretty much all actively growing, and you see them as AGN. I guess my time is coming to an end. How much do I have? Another 12:30? I'll just mention very briefly sort of the pushing of the data to even higher redshift 4 to 7. This was a pretty intensive piece of work that Mauro Stefanon did, trying to use the UltraVista DR1 data set to really look for massive galaxies at redshift above 4. And here massive galaxies, above 10 to 11, 11.2. The only reason why you could do that is by constructing an IREX selected sample, which was a lot of work. But the other very immense amount of work was to try to take into account all of the systematic effects caused by photometric redshift and stellar population synthesis modeling, effect of emission line contamination, for example. And once you account for all of these effects, basically more than 80% of the candidates go away, and you end up with, this is basically a stellar mass function above 11.2, and the green are redshift 5 to 6, the blue are redshift 4 to 5, and the red are just upper limits for redshift 6 to 7. And so without accounting for this systematic, you would conclude that there's no evolution between redshift 7 and redshift 3 in the number density of these monster galaxies, but once you do it properly, you see a huge growth in this very massive population by a factor of 100, basically from redshift 6 to redshift 3. There was one galaxy that's actually quite exciting because it's a redshift 5.5, and no matter what you do to it, it's still around 3 times 10 to the 11 solar masses. Interestingly enough, this is also MIPS detected. We tried to put a slate on it with a shooter. We didn't find anything, so I guess the jury's still out. Anyway, so sort of putting it all together, it seems to me that there might be sort of a continuum between two evolutionary paths for the formation of today's ultramassive galaxies, namely a northerly path that acts a redshift above 4, and a late path that is more active, a redshift between 2 and 4, which ultimately produce a quiescent compact galaxy, a redshift 2 or so. And the difference between these two paths is that in the sort of a late path, the central starburst, which is needed to make the compact galaxy at the end, is caused perhaps by merging two gas-rich galaxies, whereas in the early path, the universe was a lot denser at earlier times, and so the galaxy or the stellar component of the galaxy forms compact right away. Perhaps AGN is a key ingredient in both in order to quench the star formation. But ultimately, I guess you end up with a compact quiescent galaxy. And then from redshift 1, merging is the dominant mode of growth, both in stellar mass, but even more so in size. And ultimately, you end up with these ultramassive galaxies of redshift 0. This is obviously a cartoon. There's a lot of question marks here, but I guess it's a nice framework to build upon and test observationally. And I guess there's a few ways to do this in the near future and maybe the more distant future. One thing that finally is coming to an end and producing a quality catalog is the new for medium band survey 2. This has been really possible by postdoc Ryan Cybulski at Tufts. NMBS2 is just like NMBS, but 10 times wider, so about a little bit more than 5 square degrees. And so the goal there is to find these very massive, very bright galaxies above redshift 1.5 with stellar masses above 3 times 10 to the 11. So they're very rare, you need a lot of area. And from an early catalog, we were able to select about 30 candidates. This was from about 60% of the whole survey, which we observed with HST, and 5 of them we were able to observe them with both Genius and actually also Fire from Magellan. And this is a paper that was just accepted, done by my undergraduate Erin Califong, presenting the results for the spectroscopic sample. So again, they're confirmed to be above 11.5, at least 4 out of the 5 candidates. This one actually turned out to be a merging system. And you can see the diversity in their morphology. This galaxy, for example, which is the only one that is very highly star-forming with a couple of hundred solar masses per year, it's actually a very red face-on spiral galaxy with a stellar mass of, 5 times 10 to the 11 solar masses, so really ginormous. And then we have, a galaxy that, looks relatively irregular. We have an example of a minor merging here. We have an example here, you might not see that well, but there's a sort of a tail, a low surface brightness tail, indicative for recent interaction, perhaps. And this is the sort of a Niger merger system. And again, one is star forming, is really populating the extreme massive end of the main sequence of star forming galaxies at those redshifts, and the other are quiescent, and one happens to be sort of transitioning. Now, if you compare the quiescent fraction at this redshift for slightly lower stellar masses, the quiescent fraction that you find here is sort of on the very upper hand. It's quite large, and perhaps it's true, but I guess we didn't want to make any strong conclusion given the very low number of statistics here. But improvement will come with the whole NMBS2, and also with JWST, this spectroscopy of these sources will be so easy. The last 2 programs that I would like to advertise before concluding are 2 programs that I've led in the past year and a half. One is KIF, which is the K-band imaging of the frontier field. This is a program that I co-led with the Gabe Brommer Space Telescope. And basically, we imaged with Hawkeye and Mossfire all the frontier field cluster and parallel fields in the K-band. this program is completed, all the reduced data are publicly available, and you can get them from this site. The K-band image quality is very impressive. Here you have the H160, ultra deep HST image, and you can compare it with the K-band, and you see a lot of similarities. And in fact, the image quality here is the best one is like 0.3 hour seconds, so just twice the image quality of the HST. And you see here why you need the K-band and redshift above 2. You improve the photo Z enormously, and also your estimate of the stellar population properties of this galaxy. And then the last program that I would like to advertise is this HFF Deep Space, which I led at Tufts University, and basically it's the construction of the catalogs, multi-wavelength photometric catalog of the Hubble frontier fields from the UV all the way to IRAC. Again, you can search for it at this website, and this is also where we are going to release all of the catalogs early April. There'll be photometric redshift as well as stellar population properties, lensing magnitude factors, and so on. But this was a huge amount of work, and a lot of it was done by Heath Shipley and also Daniel Langabego, the other undergraduate at Tufts, as well as Ari. Because here's the HST image, a color image for this cluster, and the BCGs, the bright cluster galaxies, and the ICL are a real huge pain. And so basically, the way that we approached this was to model out these BCGs from all of the HST filters, as well as the ground-based and IRAC. So we built these models for the BCGs and the ICL, and then we subtract it out, and here you see the subtracted image, on top of which we can now apply more or less standard tools that we have developed in the sort of last decade. This has worked out very well. The quality of the catalogs are amazing. Here are the 2 clusters subtracted, and then a piece of art from Sextractor. And again, whoops. I just want to conclude, showing the redshift distributions of the 4 of the 6 clusters, as well as the parallel, and I'm sure you can pick which one is the actual cluster field with this very large spikes that corresponds to the redshift of the cluster. And the cool thing here, you have at least thousands of galaxies belonging to each cluster field. So the amount of science that you can do within those clusters, all the way down to stellar mass of 10.7, is pretty impressive. Great, amazing, very exquisite quality of the photo Z's, and again, you have a very high signal-to-noise photometry all the way down to H-band of 28 and even below. So I really want to conclude it here, advertising again that we're going to release publicly all the catalogs early April. We're pretty good we're in line with this deadline, and at this time I'd like to thank you very much for your time, and happy to take more questions.
Just out of curiosity, if you look at the Andromeda galaxy, right through the heart of it today, how much V-band extinction is there?
That's a good question.
Because when you think of the galactic center, from here to there is like 30 magnitudes of V-band extinction. And so when I think of all the dust in a dusty star-forming galaxy, when you say there's 1 to 3 magnitudes, that sounds not that dusty to me.
Right. I mean, consider the simplification that we apply to this spectral energy distribution modeling. We're assuming a screen of dust. Some of these galaxies might well be more than one stellar population. The dust could be very homogeneously distributed. Now, for a subset of those, like the Vega galaxy that I showed, you don't see, even from the HST, you see a very smooth profile. The spectral energy distribution, you can't put any dust there, pretty much. Otherwise, it would affect the SED. Whereas for other of those galaxies, especially the more dusty star-forming one, then for the very few, and I'm talking about 2, 3 of those that have HST imaging, you see that they're not as clear. I mean, they might have a couple of knots. They might look more. One object might look like a train wreck. So you have to take this modeling with a grain of salt. But the fact that there are MIPS detected, it means that there's quite a lot of dust in this system anyway, which you might not see at lower rescue in similarly massive galaxies. But yeah, the AV is really from the photons that you collect and making simple assumptions. And you know, you can also think about, you take a dusty starburst galaxy and try to put it at a redshift 3, and it will probably look just like a blob, whereas when it's in the nearby universe, it's such an amazing level of complicated structure.
Present-day spirals like Andromeda, typical values of magnitude 7/10.
No, that's not.
Consistent with the observation. Remember, the cosmic infrared background is about the same total energy as the cosmic UV plus visible, which tells you the same thing. It's a little less than magnitude.
So that's in the center?
No, if you mean through the center, through the bulge, I mean, what you think?
Yeah, through the bulge.
It's very low.
So this Casey, I couldn't really hear Rob, but I just wanted to point out that, 3 magnitudes of extinction is already considered optically thick. So at that point, you're pretty much saying, well, we saturated out what we can see in the optical. And it's certainly possible or even plausible there's a lot more serious star formation, but it's not accounting for the SADs and these things. That just consists with the infrared detection as well, the far infrared detection.
Yeah, I mean, you really need the infrared to have a better constraint of that. But again, at least with these sources, it seems that the infrared is inconsistent with being just obscure star formation.
Right, no, I agree.
Yeah.
I think that's a reasonable thing to say.
Yeah. Otherwise, given their MIPS detection, they should have been clearly detected in the Herschel data, if that's just obscure star formation.
Right, that's very good.
Yeah.
Can I ask another question?
Oh yeah.
Sure, so I'm always interested, most massive galaxies, it's really exciting. This is great stuff. So simulations must predict where these things end up today, right? I mean, if these things are 10 to the 11.5 or redshifts of order 2 or 3, then by today, I think they should grow, we say double their stellar mass or so. So they've got to be like BCGs or something, right? Like the galaxies in Coma. Which would kind of imply, like, do you see structures around these things that I redshift? Are these kind of lighthouses that you can go and mine proto groups or anything?
So are you talking about the redshift 3 to 4?
Yeah, or if you do like angular correlation functions or something, parse out what kind of halos these things are out there when they become today. Because it all hangs. What I want to find out is, do you think the story all hangs together? If you look at their clustering versus their expected evolution to the present day.
Yeah, I don't know, because we haven't done that. And I guess at those redshifts, you really have a couple of handfuls of sources, at least in this area. So I guess the number, the error on the clustering that you can get. Again, I'm not an expert on this, but I would guess it's very large. So that probably almost anything would go. I mean, probably Ryan can comment more on this.
You could do a cross correlation function to get a good signal on that.
But would the number be robust enough?
For a cross correlation signal, if the imaging is deep enough, like for NMBS2 or something, the imaging won't be.
Oh, no. For NMBS, you can only do it maybe a redshift 3.
But
if you
for
want that.
NMBS, yeah. I mean, I've done it with handful, 10-ish galaxies, and you can get something.
Okay.
Well, you can always measure something, whether or not it's,
I mean,
a
you can
robust
get-
caricature of the high redshift universes.
You can get something that's informative, I think, even with super.
But it's certainly something that we would like to do. I mean, the other thing is, with the NMBS2, at least in the redshift range 1.5 to 3, that's also one of the things that we would like to do. I mean, we expect 70 galaxies above 11.5, and if you go to a little bit, factor of 2 less massive, hundreds. So there are certainly the statistics will be larger and good to do that. But again, I guess one point here. Yeah, I guess when you approach it from a redshift 3 to 4, I look at the very, very most massive galaxies that I can find. Well, yeah, they better be in massive halos, I guess. If not, that will be quite interesting. I mean, the other thing that you want to take into consider is that it might not be the case for the star-forming galaxies, but I think a redshift above 3, I guess models are not really able to produce these massive quiescent galaxies that now you guys have confirmed the existence of. So there's already some sort of tension there, I guess.
Yeah.
Yeah, I mean, that's a good point.
All right, so one last point.
If you get us for the halo masses from the clustering, at least you can see where those end up today. If that would predict, I mean, I suspect these things have got to be the centers of pretty big galaxy clusters today.
Well, the better be.
Yeah, right, they better be, right?
I think the number densities are consistent. So just one last question from
Is there
Rob.
still time?
Yeah, just,
So, I mean, it's a corollary of Casey's question. You showed this really impressive result that above redshifts 3.2 or something, all of these practically host luminous AGNs. Have you thought, does that mean if you went out instead of trying to find massive galaxies, you looked at the luminous AGNs at those and looked at the host galaxies, you recover the same population?
That's a very good point. We haven't done that, but it's a good point. Arguably, I guess, if the claim is correct.
Well, there's so little cosmic time at that point, it almost all have to be happening simultaneously.
Yeah, I mean, their results, to me, was very surprising. I wasn't expecting to find that. But at some point, I guess, all of the massive, ultramassive galaxies today have huge supermassive black holes at their center, and they must have formed at some point. And probably that's the time when their growth is most active. But yeah, there's the other thing that it would be nice to do is to do that same analysis, well, obviously better, but also to lower stellar masses as well, to sort of see what's happening and when those stellar masses, the supermassive black holes mostly grow. Again, here I guess the approach is from a mass complete sample, as complete as it can be, I suppose.
all right, well, let's thank Danilo again.
Thank you very much.